Over the last 3 sessions, you've learned about objects and methods, but so far these were all instances of a single class. This is going to change in this session. We're going to introduce class hierarchies of classes that extend each other. An important aspect, once you have class hierarchies, is the model of evaluation, because then the actual method called might depend on the runtime type of the receiver of that method. This concept is called dynamic binding. It's one of the standard concepts in object-oriented programming. And you're going to find out how our model of term rewriting actually already naturally supports this concept. So dynamic binding and term rewriting go very naturally together.
In the last session we have looked in depth at a lot of different aspects of a single class. What we're going to do in this session is generalize that so that we now look at class hierarchies where more than one class cooperates to achieve a certain task. So as a running example in this session, we consider the task of writing a set of classes that implement sets of integers, and these integer set would be called int set and support 2 operations: include, to include an element x in the int set, and contains, which is a test whether an element x is a member of the set. So to do that, I will open a fresh worksheet, call it int sets, and add the definition of the class here. What you see, what's particular, is that we've given you 2 definitions of functions, but they do not have a body. The equals is missing and the body is missing, and that's permissible as long as the class is abstract. If I would remove the abstract, I would get a problem which would say class inset needs to be abstract since method contains is not defined and method include is not defined. So let's add the abstract again. So you've seen that abstract classes can contain members which are missing an implementation. On the other hand, we create instances of an abstract class with the operator new. So if you would try that, write here new int set, I will get an error which says that the class int set is abstract and cannot be instantiated. So since int set is incomplete, how would we implement it? Well, one way to do that would be using the binary tree data structure. In that data structure there are 2 types of possible tree. A tree that represents the empty set, and a tree that consists of an integer and 2 subtrees. And the idea would be that you keep always the invariant, that the trees are sorted. So that means that if I give you an example here, we would have a tree, let's say, with a 7, and that would have 2 subtrees, and here we would maybe have an 11, and here we would have a 5, and then the 11 could have another one, 9. And the rest ones would all be empty. So that's an example of a binary tree, and the invariant that we want to maintain is that for each node, the nodes on the right-hand side of this node all have integer values that are higher than the node, whereas the nodes on the left-hand side all have values that are less than the node. Note that this will make it easier later on to implement the contains test that determines whether a given value is in the tree. So let's start with the empty tree here. The empty tree is very simple to implement. We would simply say that contains is always false, because the empty tree cannot contain any value, whereas include is a method that returns an int set. So what set would it return? Well, it would return a non-empty set to be defined that contains the given element and 2 empty subtrees. So going from the empty set to an include set would give us a set like that contains a single node and 2 empty subnodes. Let's put that class into the worksheet. Now, it still remains to define what a non-empty set would be. A non-empty set in that implementation would be represented by a class non-empty that takes an element, that's the integer stored in the node, and a left and a right subtree, which is in each case an int set. And the implementation of contains and includes now makes use of the sorted criterion of trees. So that means that for contains we always have to look only in one of the possible subtrees. If the given number x is less than the current element value, then we know we will have to look in the left subtree here, whereas if it's greater, we know we will have to look in the right subtree. If it's neither less nor greater, then it must be equal, and in this case we have found the element. The include method follows a similar algorithm. If the element to be added is less than the element in the tree, then we need to include it in the left subtree. If it is greater, we need to include it in the right subtree, and otherwise the element is already in the tree and we can return the tree as is. There's nothing that needs to be added. One important aspect here is that we are still purely functional. There's no mutation. So when I say we include an element in the left subtree, what I really mean that we create a new tree that contains the previous element of the tree and a larger left subtree where x is included in the previous left subtree and the current subtree on the right. So visually, if I would say include the number 3 in the tree that we see here, then what would happen is I would create a new node 3 with 2 empty subtrees. That subtree would be the left subtree of a new node with element 5 and an empty right-hand subtree. And finally my tree would be a new tree with the as before the node 7 as the node and the same as the right-hand side tree here. So we see that now we really have two trees, the old one and the new one after the include. The two trees share the subtree here on the right-hand side, but they differ in the left tree, where on the new tree we have a 3 in the leftmost bottom corner, whereas for the old tree we just have 2 empty trees. One way these data structures are called, they're called persistent data structures. Because even when we do changes, or so-called changes in quotes, to a data structure, the old version of the data structure is still maintained. It doesn't go away. And persistent data structures are actually one of the cornerstone of scaling functional programming up to collections and the like. So let's take the definition of class non-empty and also add it in the worksheet so that we can test something. So now instead of new int set, I would create a set by saying, well, this would be maybe new non-empty of 3, new empty, new empty. So it would be my first set, and it would give me a non-empty set, and I could then write things like include 4, and that would give me an int set, which is another non-empty set. Now, before we go further, let's add a toString operation to our set so that we can actually see what sets we have created here. We need two definitions of toString, one in empty and one in non-empty. For empty, how would we define toString? Well, let me just define it in a very minimalistic way to give you a period. For non-empty, I want to define toString as follows. I want to say it should be an open brace followed by the description of the left element, followed by the sorry, as follows. It should be an open brace followed by the string value of the left subtree, then the element in the middle, then the right subtree, and then a closing brace. If we do that, then we see that here we get a sort of visual representation of our trees. So the first T1 would be the element tree and an empty tree to the left and right, whereas T2 would be the root of T2 would be 3. The right subtree is a tree that has 4 as its element. So we see that this tree in particular has maintained the invariant that trees are sorted. So one new thing you see here is that both empty and non-empty extend inset. So extension means that these two classes are subclasses of the base class inset. One consequence of that is that the types empty and non-empty conform to the type inset. What that means is that an object of type empty or non-empty can be used wherever an object of type inset is required. Some more terminology. We say inset is the superclass of empty and non-empty, and empty and non-empty are the subclasses of inset. In Scala, any class that you can define extends another class. Even for a class like rational, where you didn't give an extends clause, there is a superclass. So if no explicit superclass is given, the standard class object in the Java package java-lang is assumed. Object is the root class of all Java classes and also of all user-defined Scala classes. If you take the direct superclass of a class and then its superclass and so on, so all the direct and indirect superclasses of a class C, then these are called the base classes of C. So for instance, the base classes of class non-empty are inset and then object. So what you've seen in the example is that the definitions of contains and include in classes empty and non-empty implement the abstract functions in the base class inset. They were not defined in inset, but they are implemented in the subclasses empty and non-empty. It's also possible to redefine an existing non-abstract definition of a superclass in a subclass, but then you have to use override. So in this example here you see the difference. If you write in the base class foo equals 1, and then you redefine foo in the subclass which extends base, then you have to put an override. So let me demonstrate that to you in this worksheet. We have two classes, a base class and a subclass, and each of these classes have two members named foo and bar. The bar member in class sub implements the abstract definition of bar in class base, whereas the foo member replaces the concrete definition of foo in class base. If a member replaces or overrides a definition in a superclass, then the override here is mandatory. So let's say I leave that out, compile, then we will get an error which says overriding method foo in class base. The method foo here needs an override modifier. So why is that? Why here Scala is actually more picky than Java? Well, the reason is that sometimes you do not really know what methods you do inherit. So you might actually accidentally override a method in a base class, and in that case it's good that you have to be explicit about it. There's an added benefit, namely when you intend to override, but let's say you can't remember the name correctly, or you get the numbers of parameters wrong, or things like that. So if I write something like that, override def foo2, then I get an error again where we say, oh, method foo2 overrides nothing. So in that case, the override will give me the opposite protection, which says when I write override, then I want to be sure that in fact I do override another definition. For methods that implement definitions in base classes, the override is optional. You can write it if you want to, and in that case you will be warned in the same way. So if I write bar2, I will get an error as before. But you don't have to do that. So you don't need to write the override. You could just write def bar, and that's usually less noisy, so preferred. So let's get back to the intsets example. One thing to improve would be the status of the empty inset class. You could argue that there's really only a single empty inset, so it seems overkill to have the user create many instances of it. And in fact, that's very easy to achieve in Scala. You just use an object definition instead of a class definition as before. So this object definition is exactly the same as the class definition, except that instead of the keyword class, you use object. And that will define a singleton object named empty. There is only one of them, and you don't need or can create that explicitly with new. So the object empty simply exists. Technically, it will be created the first time you reference it. You reference the object simply by naming it with empty. So empty here and here replaces the creation of new empty that we had before. In terms of evaluation, singleton objects are values, so empty is already a value. There's no evaluation step that needs to be performed. So since we are already looking at objects, let's take a quick excursion and look at what a program would be in Scala. So far we've executed all Scala code from the REPL or the worksheet, but it's also possible to create standalone applications. Each such applications would contain an object, and that object contains a main method. Let's look at this with the mandatory Hello World program written in Scala. So you would write an object, name it hello. It has a main method. Then, as in Java, that main method will have to take an array of string. You can ignore that for the time being. And the body of the main method would be a println with hello world. Once you compile this program, you can start it from the command line simply with Scala and then hello. Or you could also use Java and hello. They would do the same thing in this case. So let me demonstrate that in Eclipse. So we create in the week 3 package, this time not a worksheet, but a Scala object. Call it hello. And then we have to add the main function, which takes this. And it would print something. We can run this program as a program using the green arrow here. So we run it as a Scala application, and we see on the console hello world. So that's how you would run full programs in Scala from Eclipse. So let's do an exercise. The task is to add a new method to our inset class hierarchy. The method should take the union of a set and some other set. So you should extend the class inset to be the following abstract class and implement that. So how would we go about that? Let's first start with the abstract class. So here's the signature of union, and now we get 2 errors because we have to implement it in the 2 subclasses. So let's start with empty. What would the union of an empty set and some other set be? Well, that's very simple. Empty set union some other set is always the other set. So for non-empty sets, how would we define union in this case? Well, the idea is that we split a set into its constituents. So we have the left inset, the right inset, and the element. Let's form the union instead from something that is smaller, so one of the subsets. Let's start with left and do union right. So that would give us the set without the initial element. Then let's finally give the union of the other set. And as a last action, let's include the element back into the set. So the new union has all the parts of the previous ones. It contains the left set, it contains the right set, it contains the element, and it contains the other set. So it's very easy to convince ourselves that indeed the the result set here would have all the elements of the union and would have no other elements. But there's another concern, and that is, well, how do we know that this recursion actually terminates? Because after all, union calls union, and we've seen already cases where calling yourself again would not terminate. So the argument we could make here is to say, well, every call to union is actually on something that is smaller than the set we started with. The first call to union was on the left subtree here, and obviously that set is smaller than the whole non-empty set. The second call to union was on the union on left and right, and that again contains one element less than the full set that we have here. Because every call to union is on a set that is smaller, it follows that at some point we have to reach 0, and if the set is 0, then we fall back to the case of empty sets where the union is immediate. We just return the other set. So that's how we convince ourselves that the union operations that we do here are in fact terminating, and once those are terminating, we can safely add element back with an include operation as before. What object-oriented languages do in this case, Scala included, is to use the dynamic method dispatch model. That means that the code that's invoked by a method call depends on the runtime type of the object that contains the method. I believe that's best shown in an example. So let's say you have the code empty contains 1. What do? Well, you look up the contains method in empty. Remember that was an object empty, and we had a def contains y equals false. That was its definition. So looking up that method and performing the necessary substitutions, we get false. Here's another evaluation using non-empty. We would have the set non-empty 7 empty empty, and we ask whether it contains 7. So if we look back at the definition of contains in non-empty, that's what we see here. And if we apply our substitution rules, then it means that this call of the method will be replaced by the right-hand side of the contains method, which you see here, and at the same time the substitutions of the parameters of the class and the method and the self-reference, so the 3 elements that you see here. If we perform this substitution, we arrive at this expression here. So instead of x and elem, we see 7 in each case, and instead of the this, we see new non-empty 7 empty empty. If we perform the simplification, we get that 7 is neither less nor greater than 7, so we fall into the else case, and we get true. So for the end of this session, here's something to ponder. You've seen that dynamic dispatch of methods in object-oriented languages is actually quite similar to calls of higher-order functions in pure functional languages. The similarity is that in both cases, the code that gets executed on a function or method call is not known statically. It's not apparent from the name or the type of the thing you called, but it is determined by the runtime value that is passed. So it's a fair question whether we can implement one concept in terms of the other. Can we maybe implement objects in terms of higher order functions? Or can we implement higher order functions in terms of objects? Or can we maybe go both ways? It's a question that is fairly open and that has a range of possible answers. So I just let you with that think a little bit about it and maybe discuss with others.